A bag of diamond powder can cost less than a dinner. Pack it into a thimble-sized cell, surround it with compressed salt, and squeeze it from 6 directions at nearly 1 million pounds per square inch. In one industrial process, about 10 minutes later, those loose diamond grains emerge as a black cutting body built to drill through rock. Other diamonds begin 150 kilometers beneath ancient continents. Another begins as carbon-containing gas inside glowing plasma, and none of them began as compressed coal. Same element. 4 completely different ways to make it useful. The familiar explanation says that carbon is buried underground, squeezed by pressure, and slowly becomes diamond. That is not entirely wrong. It is simply missing the part that matters most. Carbon is one of the most common elements around us. It appears in living tissue, fuels, soot, graphite, carbon dioxide, and countless manufactured materials. A diamond is not extraordinary because its ingredient is rare. It is extraordinary because of how that ingredient is arranged. In graphite, carbon atoms form flat sheets. The bonds inside each sheet are strong, but the layers can slide across one another. That is why graphite is soft enough to leave a mark on paper. Inside diamond, each carbon atom is bonded into a rigid three-dimensional network. Instead of sliding layers, the structure extends in every direction. Same carbon, different architecture. That atomic structure makes diamond the hardest, naturally occurring mineral on the Mohs scale. But hardness is one of the most misunderstood words in materials science. Hardness means resistance to scratching. It does not mean that a diamond cannot break. A single diamond crystal contains specific internal directions called cleavage planes. If force reaches the crystal at the correct angle, a crack can travel along one of those planes and split it. The material can scratch almost every natural mineral on Earth and still be shattered by one carefully placed blow. Weakness eventually became a manufacturing tool. Long before computerized scanners and industrial lasers, diamond cutters learned to split rough crystals by working with their internal structure instead of fighting it. But before anyone could cut a natural diamond, Earth had to make one and somehow bring it within reach. Most gem-quality natural diamonds formed beneath the oldest, most stable parts of continents, in thick sections of mantle rock extending far below the crust. The majority originated roughly 140 to 200 kilometers beneath the surface. Some rare diamonds came from even greater depths. The pressure there is enormous, and the temperature is far beyond anything humans encounter at the surface. But pressure alone does not automatically convert buried carbon into diamond. The chemistry also has to be correct. Evidence preserved inside natural diamonds suggests that many grew from carbon-bearing fluids or melts moving through mantle rock. Under suitable conditions, carbon separated from that material and joined the expanding diamond crystal. There is no continuous underground diamond layer. There is no lake of liquid diamond beneath a mine. There are only rare pockets where pressure, temperature, chemistry, and surrounding rock all allow the diamond structure to form and remain stable. Some natural diamonds are more than 3 billion years old. They existed before dinosaurs, before forests, and before most of the life forms familiar to us. That age exposes the problem with the compressed coal story. Coal forms from accumulated biological material relatively close to Earth's surface. Natural diamonds generally form much deeper in the mantle. Many diamonds are also far older than the plant life that produced the world's major coal deposits. Most diamonds were never coal. They were already mantle crystals before coal-forming forests existed. Tiny pieces of material became trapped inside some diamonds as they grew. In jewelry, these inclusions may reduce clarity and lower the stone's grade. To geologists, the same inclusion can be priceless. It may preserve minerals or chemical evidence from a part of Earth that humans cannot visit, drill into, or directly sample. A cloudy point inside a diamond can be a sealed message from the deep mantle. But forming the crystal does not solve the transportation problem. A diamond located 150 kilometers underground is not merely difficult to mine. It is completely unreachable. Something has to carry it upward. That job is usually performed by kimberlite, a rare type of volcanic rock originating deep within Earth. As kimberlite magma rises, it tears fragments from the mantle and transports them toward the surface. Some of those fragments contain diamonds. The eruption does not create most of the diamonds it carries. The crystals may be billions of years older than the volcanic material surrounding them. Kimberlite is not the factory. It is the elevator. No confirmed kimberlite eruption has been witnessed by humans. Geological evidence indicates that the ascent could be extremely rapid and violent. That speed may have helped preserve the diamonds. Diamond is stable under the high pressures of the mantle. As it approaches the surface, those conditions disappear. A slow journey would give the crystal more opportunity to react, transform, or be destroyed. Kimberlite delivered the diamonds quickly enough for some of them to survive. Over time, erosion exposed these volcanic deposits. Some diamonds remained inside the original kimberlite. Others were washed into riverbeds, coastal sediments, and offshore gravel. That is why diamond mines can look completely different from one another. Some operations excavate enormous open pits around kimberlite pipes. Others follow the deposit underground. Alluvial mines process river sediment, while marine vessels recover diamond-bearing gravel from the ocean floor. None of them pull polished gemstones directly from the ground. They recover ore. Inside a processing plant, the rock is crushed in controlled stages to release diamonds from the surrounding material. The word controlled is important. If the crushing is too gentle, valuable diamonds remain locked inside pieces of rock. If it is too aggressive, the equipment can fracture the stones it is supposed to recover. A large diamond can survive billions of years underground, and an explosive volcanic journey then be destroyed in seconds by a badly adjusted crusher. Once the material has been reduced to manageable sizes, screening and density separation systems remove much of the waste. Many modern recovery plants also use X-ray sorting. Some diamonds respond when exposed to X-rays. Sensors detect that response, and a mechanical system or burst of air separates the suspected stone from the passing material. By this stage, the diamond has survived the mantle, a volcanic eruption, erosion, excavation, crushing, and industrial sorting. It still does not look ready for a ring. A rough diamond may be irregular, coated, fractured, or cloudy. Its most valuable finished form is not always obvious from the outside. Before cutting begins, planners examine its shape, internal inclusions, stress, and crystallographic direction. Modern systems can scan the rough stone and generate several possible cutting plans. Each plan creates a trade-off. Preserving more weight may leave an inclusion visible. Removing the inclusion may improve clarity, but produce a smaller stone. One plan may create a single large diamond. Another may divide the same rough crystal into several smaller stones with greater combined value. The cutter is not simply revealing the object hidden inside. The cutter is deciding which version of the diamond will exist. Lasers or diamond saws divide the rough according to the selected plan. Brooding forms the outer edge. Individual facets are then ground and polished using diamond abrasive. Ordinary abrasives are not efficient enough. To manufacture diamond, factories repeatedly use more diamond. The finished stone sparkles, not because anything has been added to its surface, but because material has been removed at carefully calculated angles. Light enters the diamond and changes direction. Some of it reflects from the internal facets and returns through the top. Some separates into flashes of spectral color. As the stone, viewer, or light source moves, bright and dark areas change rapidly. Those effects are described as brightness, fire, and scintillation. A poorly proportioned stone allows too much light to escape through the bottom or sides. A carefully proportioned stone returns more light toward the viewer. The natural crystal provides the raw material. The cut creates the performance. Subscribe for more manufacturing deep dives because the next factory grows diamond from gas. A laboratory-grown diamond is not glass, cubic zirconia, or moissanite. Those materials may resemble diamond, but they have different chemical compositions and physical structures. A laboratory-grown diamond is made from carbon atoms arranged in the diamond crystal lattice. Its basic material is real diamond. The difference is its growth history. Instead of forming in the mantle and traveling upward inside volcanic rock, it develops inside a controlled manufacturing system. This is why a basic handheld diamond tester may confirm that a stone behaves like diamond without revealing whether it grew inside Earth or inside a factory. The factory has not produced an imitation. It has reproduced the crystal structure. There are two main methods for growing gem-quality laboratory diamonds: HPHT and CVD. HPHT means high pressure, high temperature. A small diamond seed is placed inside a growth capsule with a source of highly purified carbon. The capsule also contains a metallic flux, commonly involving iron, nickel, cobalt, or a combination of metals. A specialized press subjects the assembly to pressure above roughly 870,000 pounds per square inch while raising the temperature to approximately 1,300 to 1,600 degrees Celsius. Under those conditions, the metal melts and dissolves the carbon source. The interior of the capsule is designed with a temperature difference. Carbon dissolves in the hotter region, moves through the liquid metal, and reaches the cooler diamond seed. The carbon atoms leave the metal and attach themselves to the seed's existing crystal lattice. The seed gradually becomes a larger diamond. The machine is not carving a gemstone from a solid block. It is extending an atomic pattern, layer after layer. The seed provides the blueprint, and the carbon supplies the building material. Growing a gem-sized HPHT crystal normally takes days or weeks, depending on the desired size and quality. Does not mean Earth spent billions of years actively building every natural diamond. The age of a natural diamond tells us how long ago it formed, not necessarily how long the actual crystallization took. Our laboratory process does not fast-forward an identical geological journey. It creates a smaller, controlled environment in which carbon can grow in the same basic crystal structure. CVD, or chemical vapor deposition, reaches that structure without the immense pressure used by HPHT. Thin slices of diamond are placed inside a low-pressure reaction chamber. These plates act as seeds. The chamber is filled mainly with hydrogen and a small amount of a carbon-containing gas, commonly methane. Microwave energy activates the gas and creates a glowing plasma above the seeds. Inside that plasma, gas molecules break apart. Reactive carbon reaches the diamond surfaces and attaches to the existing lattice. The diamond grows upward from the plates. It is assembled from gas, atom by atom. The reactor operates at a much lower pressure than an HPHT press, although the seeds are still heated to roughly 900 to 1,200 degrees Celsius. The process may be paused, so the growing surface can be cleaned or prepared before the seeds return to the chamber. Depending on the intended result, the material may also undergo additional treatment after growth. The central challenge is not simply delivering carbon to the seed, it is preventing that carbon from becoming the wrong kind of carbon. Carbon can form graphite and other non-diamond structures. Hydrogen and carefully controlled plasma conditions help remove unwanted carbon while allowing the diamond lattice to continue growing. A CVD reactor succeeds by controlling which atomic arrangement survives. After several weeks, the chamber can produce rough diamond material thick enough to be removed from the seeds. But it does not emerge as a finished round brilliant. The grown material must still be scanned, divided, shaped, faceted, polished, cleaned, and inspected. Natural HPHT and CVD diamonds can share the same basic crystal structure, but the different environments leave different evidence behind. Growth patterns, trace elements, fluorescence behavior, internal strain, and spectroscopic features can reveal whether a diamond formed naturally or through a particular laboratory process. A polished surface may hide the manufacturing history from the human eye. It does not erase that history from the crystal, yet gem-quality diamonds are only one branch of synthetic diamond manufacturing. By volume, the industrial side is much larger. Synthetic material accounts for more than 99% of industrial diamond production and consumption worldwide. That does not mean 99% of every diamond sold as jewelry is synthetic. It means the enormous market for diamond abrasives, cutting tools, grinding materials, and industrial components is overwhelmingly supplied by factories rather than mines. Most industrial diamond will never be transparent. It will never receive 57 or 58 carefully polished facets. It will never sit inside a ring. Its job is not to return light. Its job is to survive punishment. Industrial manufacturers can produce microscopic synthetic diamond crystals in enormous quantities. The resulting powder is used in grinding wheels, polishing compounds, saw blades, machining systems, and abrasive tools. Small bags can be surprisingly inexpensive. But loose diamond powder cannot drill through rock. The separate grains must first become one usable component. This introduces a fourth process: polycrystalline diamond manufacturing. Unlike HPHT gem growth, this process does not begin with ordinary carbon and grow one continuous crystal. The starting powder is already diamond. The factory's job is to bind thousands of microscopic diamond crystals into a dense industrial body. In one manufacturing system, diamond powder is placed inside a small metal cup against a cobalt-cemented tungsten carbide substrate. The carbide provides a tough supporting base. It can also become the mounting surface used to attach the finished cutter to a drill bit. The cobalt inside that base has a second function. When the cell reaches extreme temperature and pressure, some of the cobalt melts and moves into the spaces between the diamond grains. It acts as a catalyst for the sintering process, helping the individual grains form diamond-to-diamond bonds. The tiny reaction cell is surrounded by materials that appear almost absurdly ordinary beside the machine required to compress them. In the process demonstrated at one major industrial diamond facility, components made from compressed salt help position and support the internal molds. A talc-based material forms part of the pressure gasket around the cell. Metal contacts allow electrical current to pass through a resistive heater surrounding the central assembly. Then the package enters a cubic press. The machine surrounds the reaction cell with 6 massive anvils. Each one moves toward the center, concentrating force onto an object small enough to hold between 2 fingers. Pressure approaches 1 million pounds per square inch. Electrical current heats the interior beyond 1,000 degrees Celsius. The cell may be tiny. The forces required to control it are not. Presses operating under these conditions are isolated behind protective structures because components are being pushed close to their mechanical limits. In the facility's demonstrated process, the high-pressure cycle lasts roughly 10 minutes. But the machine has not reproduced the growth of a natural gemstone in 10 minutes. The powder was already diamond before it entered the press. What emerges is a polycrystalline diamond compact, commonly shortened to PCD. When manufactured as a cutting element for drilling, it is often called a PDC. The press has transformed countless loose diamond grains into one working body, and the random orientation of those grains provides an advantage that a large, clear, single crystal does not have. Remember the cleavage planes inside a natural diamond? In a single crystal, a crack may find a favorable direction and continue through the structure. Inside polycrystalline diamond, the path encounters grain boundaries and neighboring crystals facing different directions. One grain's weak direction does not necessarily line up with the next. The crack loses its straight road. Jewelry usually wants one visually clean crystal. Industry often wants thousands of crystals interrupting one another's weaknesses, does not make PCD indestructible. High temperatures can degrade the material. Repeated impact can damage it. Stress can form near the connection between the diamond layer and tungsten carbide base. But properly engineered PCD provides exceptional resistance to abrasive wear, while offering a structure better suited to the forces experienced by many industrial tools. When the press opens, the compact remains sealed inside the compressed cell materials and metal casing. Workers break away the surrounding gasket and recover the small cup. Silicon carbide blasting can remove softer surrounding material without significantly scratching the diamond surface. Then comes the same manufacturing problem faced by gemstone cutters. The finished compact is so hard that shaping it requires diamond abrasives. Computer-controlled grinding and polishing machines bring the cutter to the exact dimensions required for its final application. For drilling tools, the tungsten carbide substrate usually remains attached. The diamond layer meets the rock. The carbide supports it from behind and provides a practical way to mount the cutter onto the drill body. As the bit rotates, the PDC elements shear through abrasive formations that would rapidly wear many conventional tool materials. The diamond is not there because it cannot be destroyed. It is there because replacing a worn drill bit thousands of meters underground is expensive. The same polycrystalline structure can be manufactured into bearing surfaces designed for low friction and extreme wear resistance. Diamond-on-diamond bearings can operate in harsh environments where grease is undesirable, difficult to maintain, or likely to become contaminated. Then there is one of the smallest and strangest industrial applications, the 3D printer nozzle. Ordinary plastic filament is not always gentle. Materials reinforced with chopped carbon fiber, glass fiber, ceramics, or other abrasive particles can slowly grind away the inside of a metal nozzle. The filament begins machining the machine that is printing it. As the opening wears larger, extrusion becomes less accurate. Fine details change, dimensions drift, and the nozzle eventually needs replacement. One solution is a nozzle containing a solid polycrystalline diamond tip. Its wear resistance helps the tiny opening maintain its dimensions. Diamond's high thermal conductivity also helps transfer heat from the printer's hot end into the filament. The same class of material used to cut through underground rock can guide molten plastic through an opening smaller than a millimeter. At one scale, diamond helps create a deep borehole. At another, it controls a line of plastic thinner than a paperclip. The material did not change. The engineering around it did. That is why the question, how are diamonds made, does not have one answer. Natural diamond grows from carbon-bearing material in rare mantle environments and reaches the surface through volcanic transport. HPHT manufacturing dissolves carbon in molten metal and grows a single crystal onto a seed under extreme pressure. CVD manufacturing breaks apart gas inside plasma and deposits carbon onto diamond plates. PCD manufacturing begins with diamond powder and sinters, thousands of grains into a dark industrial structure. These processes do not recreate one another. They solve different problems. Nature creates a crystal and stores it beneath an ancient continent. A gem laboratory creates a controlled environment for crystal growth. An industrial press takes existing crystals and redesigns how they work together. All of them depend on the same fundamental principle. A diamond is not simply carbon under pressure. The pressure must be correct. The temperature must be correct. The chemical environment must favor diamond instead of graphite. The crystal must grow or bond in a useful structure. Then manufacturers must decide what the material is supposed to do. Should it return light? Should it resist scratching? Should it interrupt cracks? Should it support a drill? Should it survive abrasive filament passing through a microscopic opening? Remember the bag of powder from the beginning? The strange part was never that something inexpensive could be placed inside an enormous machine. The strange part was that those grains were already real diamond. The press did not make them more genuine, it made them more useful together. A natural gemstone shows what Earth can build. A laboratory-grown crystal shows that humans can reproduce the atomic structure. A black polycrystalline cutter shows that engineers can redesign the structure for a completely different kind of survival. One crystal for light, thousands of crystals for punishment. The ingredient was never the remarkable part. The structure was. Subscribe for more deep dive stories about how extraordinary materials are made, and share this with someone who still thinks diamonds are compressed coal. Which process surprised you most? The volcanic journey, growing diamond from gas, or pressing industrial diamond from powder? And if you want to keep following the hidden processes behind the materials around us, watch the next video on screen.